Walking is a fundamental human action. Each day, billions of people take trillions of steps across the planet. Every time a foot presses down onto the ground, it exerts a force. This force represents a small amount of mechanical energy. For a long time, this energy simply dissipated into the ground, as heat and sound, unnoticed and unused. Engineers and scientists have started to ask a simple question: can we capture this energy? Can we turn the simple act of walking into a source of electricity? This idea is known as kinetic, or walking energy harvesting. The concept is straightforward and appealing. It taps into an activity that people already do every day without needing extra effort or fuel. The reason this idea matters is not because it will replace our large power plants. Instead, its importance lies in powering the world of small electronics that is growing all around us. The tiny sensors in our smart homes, the health trackers on our wrists, the lights that guide our way in public spaces, these devices often require very little power to operate. If we could generate that power locally right where it is needed, we could reduce our reliance on batteries. This would make devices more self-sufficient. Lower maintenance costs reduce the environmental impact of battery production and disposal, one small step at a time. Imagine a world where your shoes could help charge your fitness tracker, or where a busy train station floor powers its own emergency lighting. This is the promise of walking energy harvesting. It is a form of decentralized power generation, where many small contributions add up. One of the most common methods for turning a step into electricity uses a special class of materials with a unique property. These are called piezoelectric materials. The name comes from the Greek word piezein, which means to squeeze or press. When you apply mechanical stress to a piezoelectric material, by squeezing it, it generates a small electrical voltage across its surfaces. When you apply mechanical stress to a piezoelectric material, by bending it, it generates a small electrical voltage across its surfaces. When you apply mechanical stress to a piezoelectric material, by pressing on it, it generates a small electrical voltage across its surfaces. This phenomenon is known as the piezoelectric effect. It is a direct conversion of mechanical energy into electrical energy. Many familiar materials, including certain types of crystals like quartz and some man-made ceramics, exhibit this useful property. Imagine placing a small, flat piece of piezoelectric ceramic inside the heel of a shoe. Every time you take a step, your body weight presses down on the heel, compressing the ceramic. This compression squeezes the material's internal crystal structure. That squeeze forces positive and negative charges to separate and accumulate on opposite faces. This separation of charge creates a voltage. If you connect wires to these faces, you can draw a tiny pulse of electric current. When you lift your foot, the pressure is released, and the material returns to its original shape. That return often generates another small pulse of voltage in the opposite direction. A single step does not produce a smooth, continuous flow of power. Instead, it creates a brief spike of energy. Therefore, a complete piezoelectric harvesting system needs more than just the piezoelectric material itself. It requires a small electronic circuit, known as a power management circuit. This circuit captures the electrical pulses. It converts them into a more stable form, often converting alternating current to direct current. And it stores the energy in a small storage device, such as a rechargeable battery, or a supercapacitor for later use. This method has been tested in many different forms, from inserts inside shoes to tiles embedded in floors. For example, researchers have developed flexible piezoelectric fibers that can be woven into the structure of a shoe's sole, allowing them to bend with every step and generate power. In other experiments, arrays of small piezoelectric elements are placed under a floor tile in a busy hallway, while a single element produces a minuscule amount of power, combining the output from many elements across the tile, and capturing the energy from hundreds of footsteps can start to add up to a more significant, albeit still small, amount of electricity. This video will explore the truth about energy harvesting shoes and floors. We will look at the different technologies used to convert a footstep into a useful electric current. We will examine the real numbers to understand just how much power can be generated, and what that power can realistically do. The discussion will cover the practical challenges, cost, durability, the comfort of the person walking, and show where this clever idea fits into our broader energy landscape. While the piezoelectric effect is a popular method, it is not the only way to generate electricity from a footstep. Another important technique is based on electromagnetic induction. the same fundamental principle that drives the large generators in our power plants. This method involves moving a magnet near a coil of wire. According to Faraday's law of induction, whenever a magnetic field passing through a coil of wire changes, it induces an electric current in the wire. To use this for walking, engineers design devices where a person's step causes a magnet to move relative to a coil, or vice versa. A practical example of this can be found in Kinetic floor tiles developed by companies like Pavegen. When a person steps on one of these tiles, the surface depresses by a few millimeters. This downward motion is mechanically linked to a small flywheel or a linear generator. As the device moves, it drives a set of magnets past coils of copper wire, inducing a current. When the person steps off the tile, a spring mechanism returns the surface to its original position, sometimes generating another small pulse of electricity in the process. This method can often generate more power per step than piezoelectric systems, but the devices tend to be more mechanically complex. A third, less common but promising method for harvesting walking energy is the triboelectric effect. This is the same effect that causes static electricity when you rub a balloon on your hair. When two different materials come into contact and then separate, they can exchange electrons, leaving one surface with a net positive charge and the other with a net negative charge. This charge separation creates a voltage. Engineers have designed triboelectric nanogenerators, TENGs, that use this principle, continuously generating an alternating current as charges flow back and forth. To understand the true potential of walking energy harvesting, we must look at the numbers. The power of a human footstep is surprisingly large, but the amount of electricity we can actually generate from it is very small. When a person weighing 68 kilograms, about 150 pounds, walks at a normal pace, each footstep transfers about 70 watts of mechanical power into the ground. However, this is not free energy we can simply scoop up. Most of this power is used to decelerate the body and is dissipated as heat. An energy harvester can only capture a tiny fraction of this total power. In practice, most current prototypes and commercial products generate power measured in milliwatts, which is 1/1000th of a watt. For example, a laboratory prototype of a shoe-mounted harvester might generate between 1 and 10 milliwatts on average during a steady walk. A single Kinetic floor tile, like those from Pavegen, is rated to produce around 2 to 4 watts of power, but this is the peak power generated for the brief moment of the footstep itself. The average power over time is much lower. One installation in a busy Tokyo train station found that floor mats generated about 1/10 of a watt from the step of an average person. A small efficient LED light might require around 20 to 50 milliwatts to be visibly bright. A modern smartphone, when charging, consumes several watts of power, typically between 5 and 18 watts. This means you would need the continuous output of hundreds or even thousands of footsteps on the most efficient Kinetic tiles just to charge one phone. Powering a laptop, which can require 45 watts or more, is completely out of reach. This simple comparison shows that walking energy is not a solution for high-power devices. Its utility is strictly limited to the world of low-power electronics. Therefore, the key is to match the small power supply with an equally small power demand. The growing Internet of Things is a perfect example. Beyond the physics and engineering, the success of any walking energy harvester depends heavily on the human factor. If a device makes walking uncomfortable or requires extra effort, people will not use it. The most important consideration is the metabolic cost, the amount of extra energy or calories the user has to burn to carry and operate the harvester. A perfect device would be weightless and require no extra effort to use. In reality, any added weight or resistance means the walker has to work harder. If the extra calories burned are greater than the energy value of the electricity produced, the system is a net loss. For example, early prototypes of energy harvesting backpacks required the wearer to burn significantly more energy to generate a few watts of electricity. While useful for soldiers in the field who need power and are already carrying heavy loads, it is not practical for everyday life. More successful designs focus on being metabolically transparent. Researchers have developed knee brace harvesters designed to generate power primarily during the part of the stride where the leg muscles are already working to slow the limb down. One such device, weighing about 307 grams, was shown to generate 1.6 milliwatts with almost no measurable increase in the wearer's metabolic rate. Comfort is another critical issue. A shoe insert must not cause blisters, change a person's gait, or feel lumpy underfoot. If a Kinetic tile feels spongy or unstable, people may unconsciously walk around it. Regulations like the ADA set strict standards for floor surfaces, limiting how much they can depress to keep them safe for people with mobility challenges or using wheelchairs, which adds a design constraint. Moving a promising idea from a controlled laboratory environment to the unpredictable real world is filled with engineering challenges, and walking energy harvesting is no exception. One of the most significant hurdles is durability. A device inside a shoe must withstand hundreds of thousands, if not millions, of compression cycles without breaking down. It must endure bending, twisting, moisture from sweat, and impacts from running or jumping. Floor tiles in a public space face even harsher conditions. They must support the weight of thousands of people every day, resist damage from dirt and spilled liquids, and function across a wide range of temperatures, from freezing winter nights to hot summer days. Material selection is a constant trade-off. Piezoelectric ceramics can be very efficient but brittle and may crack under repeated stress. Polymer-based piezoelectric materials are more flexible and durable, but usually generate less power. For electromagnetic systems, moving parts like bearings and springs are potential points of failure. Designing these systems to last millions of cycles without maintenance requires careful design and extensive testing. Another complex challenge is power management. The electricity from a footstep isn't a steady clean stream like a wall outlet. It comes in short, irregular, spiky bursts of voltage. This dirty power can't directly run sensitive electronics. An essential component is the Power Management Integrated Circuit, the PMIC. It must capture brief energy pulses efficiently, convert the voltage to a stable level, and store energy, while consuming very little power itself. Finally, the system must be designed for a specific purpose, balancing competing goals. For wearables, prioritize lightweight and comfort, even if that sacrifices some power output. For public floor installations, prioritize high durability and safety, with power generation as a secondary benefit. Engineering trade-offs are everywhere. Higher power output can mean a heavier device. Lower cost can mean less durable materials. A smoother walking surface can mean less efficient energy capture. Successful design needs a holistic approach from the user's foot to the final electronic device being powered. Several projects have made their way into the public eye, demonstrating the technology in real-world settings. Their projects often combine energy generation, data collection, and interactive lighting. For example, they installed a 200-tile walkway in Washington, D.C.'s DuPont Circle, where footsteps power overhead LED lights and track pedestrian flow. Given the low power output and high cost, walking energy harvesting is not a universal solution. It will not power our homes or cities. Instead, its true value is found in specific niche applications where its unique advantages, being local, battery-free, powered by human activity. The most promising area today is in powering low-energy wearable electronics. Consider a health and fitness tracker. A device that monitors steps, heart rate, or gait for medical analysis needs a continuous power supply. If powered by walking, it could operate indefinitely without the user ever needing to remember to charge it. This is particularly valuable for remote patient monitoring, where an elderly person or a child with GPS tracking shoes could have battery life extended, providing a more reliable safety net. Another strong niche is in remote or off-grid locations where replacing batteries is difficult, expensive, or impossible. Sensors along hiking trails could be kept powered by passing footsteps. In military applications, soldiers carrying heavy battery packs could reduce their load if their own movements could power essential communication gear or navigation devices. Finally, the technology has found a role in interactive architecture and marketing. The wow factor of a floor that lights up when you step on it has real value. The system's ability to also collect footfall data, counting how many people walk through an area and when, is an additional benefit for urban planning and retail analytics. Looking to the future, the field is poised for slow but steady growth, driven by advances in materials science and by shrinking power demands of electronics. The technology will likely not experience a revolutionary breakthrough that suddenly allows us to charge our phones from our shoes. Instead, its progress will be evolutionary, with incremental improvements making it more efficient, more durable, and less expensive over time. Hybrid generators combining piezoelectric, triboelectric, and electromagnetic effects can capture a wider range of motions and vibrations, boosting energy output from each step. In conclusion, making electricity from walking is real and scientifically sound, but be realistic about its capabilities. It is a smart step, not a giant leap, toward a more distributed, sustainable energy future.